Yes. Fission means what? Yes, breaking of a big nuclei into smaller fragments. So, fission, basic concept, binding energy graph. This part means what? Heavy nuclei, and binding energy per nucleon is less. If you change it to small nuclei, it will shift to this part, this zone, where binding energy per nucleon is more, stability is more. So a heavy nuclei, in this case, yes, uranium 235, check the reaction please. Uranium 235, this is 92. Fast moving neutron will hit. Outcome is what? Yes. Barium and krypton. Barium, Kr is krypton, sure. Neutrons, how many? Plus energy. Of what order? Say 200 mega electron volt. Barium, yes. Number of protons? 56. Nucleon? 140. Kr? This reaction is most probable reaction. That is why we are writing the most probable. Actually, the yield is, the percentage yield is, the graph, percentage yield on this side. If you refer to the graph, the two peaks are, yes, refer to the book, article number 28. Yes, percentage yield is of this type, the graph is of this type. The most probable for A is equal to, yes, number of nucleons approximately 90, nearby 90, that means this one, and the second one 140, that means this one. And approximate what percentage? Approximate 7%, anywhere between 5 to 10%. So this most probable reaction is say 7%, and the other reactions are 1%, 0.1%, 0.2%, 0.3%. So this reaction being most probable, that is why we are writing this. Now what does it mean? A heavy nuclei with less binding energy per nucleon splits to relatively smaller nuclei, moderate size, where binding energy per nucleon is more. And how many neutrons are available? 3 neutrons. One neutron, when it hits a nuclei uranium, from this one, no doubt you will get barium krypton, but how many neutrons are available now? 3. These 3 neutrons, when hit the nuclei, will further give how many? 3. This will also give how many? 3. This will give how many? 3. So, 1 neutron gives 3, 3 will give how many? 9, then 27. These number of neutrons will keep on increasing, and huge amount of energy can be generated. This is termed as what? Yes, chain reaction. 2 minutes with you to write. They are daughter nuclei. They are also present within the plant. Yes, that is why we need to remove it after some time. This you can write binding energy per nucleon. Along x-axis is A. Reproduction factor K. Reproduction factor, reproduction parameter K is a ratio. Yes. K is a ratio. Yes. Numerator, number of neutrons. Yes. Produced to number of neutrons. Number of neutrons lost in a given city. If the birth rate and death rate is equal, then population remains a constant. If the birth rate is more than the death rate, population will increase. If a birth rate is less, death rate is more, population will decrease. And a population of 1 lakh will reduce to 50,000, 25,000, and this number will keep on decreasing. Similarly, here also, this factor K can be equal to 1, K can be greater than 1, K can be less than 1. Case number 1. Yes. Refer to notes. Yes. K is what? Equal to 1. If K is equal to 1, what does mean? If K is equal to 1, number of neutrons produced is equal to number of neutrons lost. The operation of the reactor is said to be critical. Operation is critical. Which is what we wish it to be for steady power generation. That means nuclear power plant, we keep maintain around 1. Application, nuclear power plant. For changing the number of neutrons, you can use control rods. If you insert the control rods, then it will absorb neutrons. Neutron number will decrease. If you remove the control rods out, then absorption of neutrons will decrease. So neutron number will increase. 1. Case number 2. Yes, K greater than 1. Yes. Now operation is. What is the term used? Yes, super critical. What does it mean? K more than 1. Number of neutrons produced is more than number of neutrons lost. More energy is generated than required and you may lose control over the reaction. The term used is. If K is greater than 1, the chain reaction accelerates, resulting in explosion, underline explosion. The size of the material in the case is supercritical. This is how an atom bomb works. Explosion, condition, atom bomb. Third, case number 3, K less than 1 means what? Number of neutrons produced is less, loss is more. Is what? Yes, operation is, yes, subcritical. And working of the plant will stop. It will cease, the reaction will stop. The statement is the chain reaction gradually comes to halt. The size of the material used is subcritical. Reaction stops after some time. Time with you is 3 minutes to write. 3 minutes to write. K is equal to 1. See, you have to maintain this level that number of neutrons are equal to 1. If it is more than 1, it will lead to what? Fast chain reaction and more reactions than required and beyond your control. If it is beyond your control, it will lead to what? Explosion. That means K is equal to 1, that means everything is within your control and you are generating power as per your need. If it is less, the reaction will stop. So, like in a vehicle, you have an accelerator within your control. If it is on higher end, will lead to accident. If it is low, the vehicle will stop. Similarly, here also you maintain K is equal to 1. Refer to numerical part. Numerical number 29. Numerical is when uranium-235 undergoes fission, 0.1% of the original mass is released into energy. How much energy is released by an atom bomb which contains 10 kg of uranium-235? 2 minutes with you to solve. Given, yes, 0.1% of 10 kg is used, correct? So, step 1, mass M is equal to 0.1% of 10 kg is equal to what? 0.1 by 100 into 10 comes out to what? 10 raised to power minus 2 kg. 2. You want energy. E. Formula. Mass is converted to energy. So, E is equal to mc square. There is no reaction given in this case. The principle is given, 0.1% of the mass will be converted to energy. Mass is how much? 10 raised to power minus 2 kg SI units. Speed of light, 3 into 10 to the power 8 meter per second SI units. Yes, 3 square is 9, 10 raised to power, this is 16 minus 2 comes out to be what? 9 into 10 raised to power 14 joules. So, energy is 9 into 10 to the power 14 joule. Numerical number 30. Numerical number 30 is, what is the power output of uranium-235 reactor if it takes 30 days to use up 2 kg of fuel and if each fission gives 185 mega electron volt of usable energy? Given, material is what? Uranium-235. Mass is how much? 2 kg. Each reaction, energy per reaction. Yes. 1 mega electron volt. Number of days, 30. And what do you want to find out is power. Step 1. Find number of moles. Yes, anyone? Uranium 235. 235 grams gives you what? 1 mole. Mass is how much? 2 kg. Chemistry. 2000 grams divided by 235 grams. Find number of moles. How many moles are there? Find number of moles. Yes, 200 by 235. Eight point something. 8 point. Yes. Approximately 8.5 moles. Say 8.5. Not an issue. 2. Number of uranium 235 atoms. Yes. 1 mole has how many atoms? 6.023 into 10 power 23. So we'll have approximate value. You can, for calculation, you can take it 6 only, 10 power 23. So many atoms. Find how many atoms. That means temporarily assume this to be 6 only. 6 into 8.5. Yes? 51 into 10 power 23. So many atoms. Each atom, each reaction gives you how much energy? 185 mega electron volt per reaction, means per atom. So what is energy available? Energy available is number of atoms, so many atoms, and 185 mega electron volt per atom. So energy available is how much? 51 into 185 into 10 raised to power 23 mega electron volt. Calculation will have at the end. Per. Yes, anyone? Energy by time. Energy is how much? 51 into 185 into 10 power 23 mega electron volt. I want to change it to joule. Yes, mega means what? Mega means what? 10 raised to power 6. Electron volt means what? 1.6 into 10 raised to power minus 19 joule divided by how many days? 30 days. Change it to hours. Yes, 24 hours. Change it to minutes. 60 minutes. Change it to seconds. 60 seconds. So this is joule per second is watt. Calculate and confirm. That you get 58.3 into 10 power 6. Approximately 58 into 10 power 6 watt means 58 megawatt. 2 minutes with you for calculation.